Hey there and welcome. Today we're going to peek inside the brain's own pharmacy. We're basically going on a few special ops missions to understand how specific drugs can navigate the incredibly complex chemistry of our minds to get the job done. You ready? Let's get into it.
I mean, that's a wild question, right? How can one little thing have such a huge effect? Well, the answer is all about something called neuropharmacology, which is just the science of how drugs in our nervous system get along. And what we're going to see is how these drugs can be, unbelievably precise.
You know, the easiest way to wrap your head around this whole thing is the lock and key idea. Think of it like this. Your brain cells are covered in these tiny, tiny locks. We call them receptors. And drugs, they're basically the keys that are perfectly designed to fit them. Today, we're diving into 4 different missions, each one using a unique key for a specific lock.
All right, first up, Mission 1. The objective? We need to turn consciousness down, like way down. You know, for surgery and stuff, you need a totally reliable off switch. And that's exactly what general anesthetics are. They are the absolute masters of a targeted shutdown.
Okay, so let's meet our first agent on this mission, propofol. And its big claim to fame? It is fast. It works incredibly quickly and wears off just as fast, which gives doctors amazing control. But how does it actually work?
Okay, so here's the deal. Your brain has its own built-in braking system. It's a chemical called GABA, and its whole job is to tell your brain cells to just chill out, slow down. What propofol does is it finds the locks for GABA and basically just slams its foot on the brake pedal, making that slow down signal way, way stronger. That massive braking action is what safely powers the brain down.
And this is where it gets really cool. There's more than one way to achieve anesthesia. You've got propofol, which is hitting the brakes. But then you have something like ketamine, which does the complete opposite. It blocks one of the brain's main gas pedals. Totally different keys, totally different locks, but you end up at the same destination. It's all about knowing your target.
All right, on to mission 2. And this time, we're not shutting things down. We're more like fine-tuning. We're talking about drugs that have to rebalance the super delicate chemical signals that control how we think and feel.
So our first case study here is risperidone. It's an antipsychotic, and its mission is to help with conditions like schizophrenia by targeting a really famous chemical you've probably heard of, dopamine. See, in some conditions, the dopamine system can kind of go into overdrive.
And this is a perfect example of our lock and key idea in action. Risperidone's job is to go in and physically block a very specific dopamine lock. It's called the D2 receptor. It's literally like putting a piece of tape over a keyhole. The dopamine key is still there, floating around, but it just can't get in. The lock is blocked. And that helps calm down all that overactivity.
Okay, let's switch gears to another kind of mood mission, this one for depression. And for this, we're looking at sertraline, which is a super well-known antidepressant. It's what's called an SSRI, and its target isn't dopamine. It's another major mood player, serotonin.
So how does an SSRI actually work? Okay, picture this. Serotonin is like a little messenger carrying a note from one brain cell to another. Now, usually, right after it delivers that note, this little vacuum cleaner comes along and sucks the messenger right back up. Sertraline's whole job is to just block that vacuum. So the messenger gets to hang out in that space a little longer, delivering its message over and over again. It doesn't create more serotonin, it just makes the serotonin you already have work more efficiently.
All right, mission 3. And now we're dealing with something totally different. We're talking about an electrical storm inside the brain. That's really what a seizure is. Just this massive, chaotic surge of electrical signals firing everywhere. So the question is, how do you calm that down?
Well, the key for this mission is a drug called carbamazepine. It's an anticonvulsant, and its whole goal is to bring some calm and stability back to the brain's electrical grid. And it does that by going right to the source of the problem.
Okay, so think of your brain cells as having all these tiny little gates called sodium channels. These gates open and close to let electrical signals pass through. Now, during a seizure, these gates are just flying open and slamming shut, completely out of control. What carbamazepine does is it comes in and acts like a bouncer, locking some of those gates shut. It doesn't stop everything, but it slows things down just enough to prevent that electrical storm from spreading.
And here we go again. You can see there's more than one way to solve the problem. You've got carbamazepine, which is like a specialist. It's focused on one job, locking those sodium channel floodgates. But then you have something like valproate, which is more of a generalist. Instead of just closing one type of gate, it's like reinforcing the whole dam. It also boosts that GABA braking system we talked about earlier, a 2-for-1 deal.
And that brings us to our fourth and final mission. And honestly, this one is a straight-up rescue mission. See, with Parkinson's disease, the brain is facing a massive supply chain crisis. The very cells that make dopamine start dying off. So the mission here isn't about blocking or boosting a signal, it's about getting more supplies to the front line.
And the main tool for this job is L-DOPA. But here's the really brilliant part. L-DOPA is not dopamine. It's the precursor. It's like sending flour to a bakery instead of trying to send a finished loaf of bread. And the reason for this is pure genius.
Okay, so your brain has this incredible security system called the blood-brain barrier. It's like a VIP checkpoint that's super picky about what it lets in. And dopamine itself? Nope, can't get past the bouncer. But L-DOPA, it's got the all-access pass. So it acts like a Trojan horse. It gets snuck past the brain's defenses. And once it's inside, the brain's own factories turn it into the dopamine it needs. It's just an incredibly clever workaround.
And this is a fantastic way to see the two different strategies at play. On one hand, L-DOPA is literally refilling the tank with raw fuel. But then you have drugs like pramipexole, which are called dopamine agonists. They don't add any fuel. Instead, they're like a perfectly crafted master key. They're shaped so much like dopamine that they can just go right up to the dopamine lock and open it themselves, tricking the brain into thinking it's the real deal.
So, there you have it. 4 different missions deep inside the brain's pharmacy. So what's the one big idea to take away from all of this? It all boils down to one word: precision. And this table really lays it all out, doesn't it? We saw propofol slamming on the GABA brakes for anesthesia, risperidone putting up a shield on dopamine receptors to help with psychosis, sertraline blocking the vacuum cleaner to make serotonin more effective, carbamazepine locking down electrical gates to stop seizures, and L-DOPA smuggling in the raw materials to fight Parkinson's. Every single one, a very specific tool for a very specific job.
And that's really the heart of it. We've gone from using sledgehammers to using molecular scalpels. Modern neuropharmacology is all about this incredible nuance, finding just the right key for just the right lock to gently nudge the brain back towards balance.
And that, of course, leaves us with a huge, exciting question for the future. We are getting ridiculously good at crafting these little molecular keys. So as we get even more precise, what's next? What new doors are we going to be able to unlock in the brain? Think about it. What conditions that we think of as untreatable today might be totally manageable tomorrow? That's the incredible frontier we're standing on right now. Thanks so much for joining me.